First things first, everyone. Let's talk about what a gravitational wave actually is. Gravitational waves are ripples in the fabric of space-time caused by massive interstellar interactions.
According to general relativity, space isn't some sort of voidless box that we are all sitting in. Instead, it's more of a fabric made up of space and time woven together, like the picture you can see behind me. Planets, stars, interstellar dust, and black holes are all laying on this fabric of space-time.
When two of these massive objects interact on this fabric, they are bound to create ripples that both contract and elongate the very material that they lay on. This is the same idea in space. When two massive objects interact with each other, they cause the very fabric of space-time to temporarily warp.
For example, black hole interactions have resulted in gravitational waves because black holes are so massive. We also have pinpointed other sources as well, including a neutron star collision, like you can see here, and also supernova.
Now, let's talk a little bit about the history behind gravitational waves.
Back in 1916, Einstein's work with special and general relativity field equations formed his prediction that gravitational waves did exist. He discovered that linearized weak field equations had wave solutions.
There was more scientific work from the 70s to the 90s, which introduced further knowledge on quasi-normal modes and relativistic two-body dynamic systems. These breakthroughs in theory work enabled binary black hole mergers to be modeled and then used to predict their gravitational waves.
Now, this is one of my favorite mustaches in science. His name is Carl Schwarzschild, and he participated in some black hole research that helped with the discovery of gravitational waves. But next came actual experiments trying to detect these gravitational waves. In the 60s, scientist Dr. Joseph Weber began working with resonant mass detectors. Shortly after, interferometric detectors were studied to be used. Then proposals were made for long baseline broadband laser interferometers with increased sensitivity.
All of this work formed great success in the 2000s when initial detectors, including LIGO in the United States and TAMA 300 in Japan, were created. But wait, Jordyn, what exactly is LIGO? By the way, behind me is a map of all the gravitational wave detectors in the world, including LIGO. And now Jordyn's going to go more in depth on what LIGO actually means and what LIGO stands for.
So LIGO is an acronym for the Laser Interferometer Gravitational Wave Observatory. And this is where cosmic gravitational waves are detected by laser interferometry.
Laser interferometry is when wavelengths from lasers are used to create constructive and destructive interferences, like Young's classic double-slit experiment in physics.
The interferences are measured in order to detect any changes made by the gravitational waves. LIGO has 2 observatories in the US. Now, Kellen, why do they need both?
Well, Joey, having 2 locations makes sure that the signal detection is not caused by some sort of local disturbance rather than a true gravitational wave. Now the theory and construction of LIGO is set in stone, but has LIGO been effective in its search for gravitational waves?
That's a really good point, Kellen. The first detection was made on September 14, 2015 by LIGO and Virgo collaborations. The waveform was compared to predicted theoretical waveforms in a process called matched filtering to find a model to best fit the observed data. Joey studied the waveform trend specifically and can elaborate more on this for you.
But now, everyone, I'm going to show you guys a drawing of what the observed gravitational wave will look like and what it shows us. This trend is taken from LIGO themselves. So a black hole coalescence has 3 steps: the in-spiral, the merger, and the ring down. This is the in-spiral that I'm showing you here. So the in-spiral shows 2 black holes approaching one another. The in-spiral waves themselves go greater in strain and higher in frequency, as we can see as time goes on, reflecting the distance decreasing between the objects and the subsequent acceleration. Now, if I scroll down, here's the merger. So the merger represents the event itself. Little is known about the merger event outside of theory, but the observed data shows that the merger is the source of the most energetic waves from the event itself, as seen by the max amplitude of strain. The merger is followed closely by what we call the ring down. So the ring down is indicative of a newly formed, still oscillating black hole reaching its rest state. Similar to how a bell produces a typical noise and slowly damps over time, a black hole produces an exponentially damped gravitational wave when rang or merged. This is indicative of a new black hole becoming static.
As you all have already figured out, LIGO does a great job at detecting collisions of massive objects like black holes and neutron stars. But why should everyone care about gravitational waves?
Well, I hear that some astronomers compare LIGO to the ear of the astronomical community. And why is that?
In the past, we've primarily observed electromagnetic waves through telescopes in order to make judgments about our universe.
Unlike electromagnetic waves, gravitational waves are unobstructed as they pass through space-time. This allows us to detect events from farthest reaches of space with more clarity.
LIGO has provided a powerful new angle from which to sense space in ways our eyes can't see, and the potential for new discovery is at a maximum. Hopefully, this new way of hearing space leads us to new and exciting discoveries for unanswered questions down the road.